This is Unit 2, Video 4. In this video we will talk about two more trends which are related to each other. The first is something called electron affinity. Now the word affinity means the attraction for something. So if you have an affinity for donuts, then when you walk across a room where there's donuts at a table, then those donuts are no longer at that table after you walk across. And that's the idea. So this is like the attraction, how much you desire something or your attraction to something. Now, in our case with atoms, it'll be attraction or affinity for electrons. And electron affinity is the amount of energy released when an atom gains an electron. So we talked about ionization energy, which was losing electrons. Here we'll talk about electron affinity, gaining electrons. The units are the same, kilojoules per mole. And what happens is the electron is added to the atom. The atom becomes an ion, negatively charged ion, and becomes bigger. Now it's important to understand that electron affinities are exothermic, which means energy is released. And since it's the way to think about it as exothermic is the opposite of breaking a bond. So we said that whenever you remove an electron from an atom, it requires you to break that bond between the nucleus and the electron. And that energy has to be absorbed. You have to put energy into something to break a bond. So the opposite happens here. Energy is actually released as the bond is formed. So think of when the bond is broken, you have to put energy in. So when the opposite happens, energy is released. So think of the element thanking you with energy, releasing energy, thanking you for giving it an electron. That becomes a bond has been formed. Anytime we form bonds, energy is actually released in chemistry. So here are the trends for electron affinity. The trends in general are electron affinity increases going up, and it increases going to the right. And what you'll see is that in general this trend holds true, but there will also be exceptions. So if you take a look, for example, you'll see in general the electron affinity is increasing going up this group. So hydrogen has a high electron affinity as compared to rubidium. Now notice they are negative, and that's because negative in chemistry means released. So that negative again means released energy. You'll also see, if you go across one of the periods, say period 4 here, you'll see that in general ionization energy or electron affinities increase. Now what you'll see is that electron affinities increase until you get to the noble gases. Now noble gases, this means greater than 0, which means positive. Noble gases have positive electron affinities. The reason for this is because they don't want an electron. So anytime an element does not want an electron, you'll see a positive electron affinity. And they don't want electrons because they are already full of electrons. So this is an indication of them saying, no, do not give me the extra electron. I will not give you energy back. In fact, you have to put energy into me in order to give me that electron. That's why these are positive. You'll have to force the electron onto the atom in a strange way. You'll also see another few positives. In fact, you'll see it right here, and you'll see two more right here, and calcium is really close. And this will tell the story of the exceptions. And here they are. And the exceptions are, again, relating to the second group, which is the filled S subshell. So here it says the S subshell, when it's filled, it creates stability. And this is proof that our model of the electron configuration is correct. So the S subshell being filled is stable, and beryllium and magnesium do not want those electrons. They would rather not have them because they already have a filled S subshell. And very similar thing happens to calcium and strontium. They are slightly ambivalent. They'll go ahead and accept an electron because in the case of calcium and strontium, the atom is quite a bit bigger, so it does not make that big of a difference as compared to the smaller atoms. The same thing happens in the nitrogen group. Here it says we have a half-filled subshell, same idea that we've seen before. Again, more verification of our model. And nitrogen does not want the electron, but as you go down, you can see the trend is less pronounced in the case of the rest of the elements. Here we have a subshell, a half-filled. Remember, this is half-filled. So you don't see as big as the trend. But as you go across, you definitely see a trend. So if you were to go, say, gallium to germanium to arsenic, you definitely see it jump down. So you see this trend decrease, and then it keeps going up and up. So you see it if you compare the elements in that period. So that exception, that discontinuity is definitely there. And you want to know about this, and you want to know the reason for this. And the reason is the same as before: filled shell, subshell, and half-filled subshell. And this trend explains why the halogen group increases going up, not going down. So we saw that the group 1 alkali metals in the previous video, if you have group 1 right here, you got sodium, potassium, and so forth. Rubidium, we had lithium up there, we had rubidium and cesium. So you'll see we said that the reactivity increases as you go down, but in the case of the nonmetals, reactivity increases as you go up. This is group 17. And this is explained by electron affinity. Because electron affinity increases going up a group, the atoms want the electrons more and more as you go up. That's why fluorine, desiring the electrons so strongly, will have one of the highest reactivities of all. Fluorine is actually, you can say, the most reactive element on the periodic table is fluorine, because it stands to gain the most from accepting that electron. And here what you see, here's a little video which will show you, is we just have fluorine coming in through this tube here. This is fluorine gas, essentially just hitting some charcoal, which is carbon. Charcoal is just pure carbon. It's fuel, essentially. And there's no ignition necessary. If you simply pour the gas onto the carbon, ignition results. And that is, fluorine is really tough to contain, really tough to work with, because it's extremely reactive. And hopefully you recall our discussion about chlorine, the reactivity of chlorine as well. The last trend, which is related to electron affinity, is something called electronegativity. Now, the reason we call it electronegativity is, again, the way an electron is attracted. Except in this case, we have to talk about compounds. This is how strongly an atom attracts electrons in a compound. So eventually we'll start talking about compounds. In the case of compounds, there are bonds that are formed between the elements. So here, for example, we have a bond formed between carbon and hydrogen. Now, electronegativity talks about whether this sharing is equal or unequal, whether the carbon pulls the electrons closer to itself or whether the hydrogen pulls the electrons closer to itself. In the case of hydrogen and carbon, their electronegativities are about the same. So the pull of these electrons are about equal. If these arrows represent the pull, we'll draw the arrows about the same strength, about the same length. Except if you take a look at oxygen and hydrogen, oxygen actually has a much higher electronegativity. It pulls the electrons stronger, more strongly, and that's because it's to the right of the periodic table, and it wants electrons more than does hydrogen. So what you see here is the arrow would be much more strongly pointed this way and weakly pointed this way, because hydrogen is less desireful of the electrons than oxygen is. Oxygen is actually one of the most electronegative elements on the periodic table, as we'll see. And the general trend is actually the most electronegative elements are in the upper right-hand corner of the periodic table, and the least electronegative elements are on the bottom left. So elements that are on the bottom left, you can say that on the periodic table, the bottom left is reserved for metals, whereas the top right are the nonmetals. And we've seen this before, metals want to release electrons. They don't want to gain electrons. They want to become positive. And nonmetals want to become negative. They want to accept electrons. So nonmetals will be very electronegative. They want electrons, so they'll pull electrons toward themselves. Metals, on the other hand, will give up electrons. So this is in keeping with the rest of the trends that we've discussed. Now, the four most electronegative elements on the periodic table are in this order. Fluorine is the most electronegative. It wants the electrons the most. Oxygen is second, and nitrogen is third. And these are in red because these three, as you'll see, will form a very important basis of when we talk about compounds later on. This will be a very important trend to remember. So think of Fonkel. Chlorine is the fourth most electronegative. It's not in red because it doesn't have, it's beyond a certain threshold. And the more important idea is fluorine, oxygen, and nitrogen are actually in the previous period, which means they are quite a bit smaller, and they stand to gain much more energy if they accept that electron compared to chlorine. Notice chlorine is down here. So these guys are essentially in the league of their own, really high electronegativities. And again, here it says there are no electronegativity values for the noble gases. And the reason why is because the noble gases do not form compounds. And since electronegativity refers to how strongly you pull electrons in a compound, noble gases don't form compounds. Now this is technically not true. We have formed some compounds with noble gases, especially down here. And the compounds that have been formed, really extremely rare, and quite recently we formed compounds. They actually form between only one element, and that element is fluorine. So the noble gases, if they are to react, fluorine is the only one that's strong enough to react with them. Essentially, fluorine is able to pull the electron away from the noble gases. That's because it has such a high electronegativity. So fluorine is the boss, the king of reactivity on the periodic table. Right, let's do a few examples and then we'll wrap it up. Here it says in carbon monoxide, which is a compound, creating a bond between carbon and oxygen. Where are the electrons pulled toward carbon or toward oxygen? And all we have to do is ask ourselves which element is more electronegative, and it is oxygen. Oxygen is the second most electronegative element on the periodic table, so it'll definitely be toward the oxygen. And then here the question says, which bond will cause the biggest difference in electronegativity? So in this case, when the atoms pull the electrons toward themselves, there'll be a difference that's created. And which one creates the biggest difference? Well, we know fluorine is the most electronegative, so it pulls the strongest. So what we need to ask ourselves, between oxygen, carbon, and hydrogen, which is the least electronegative? And that would be hydrogen. The way we know this is because electronegativity increases as you go this way on the periodic table, and hydrogen is sitting right here. And here is hydrogen. We have carbon and oxygen. Carbon's right here, and oxygen is not too far away. So because hydrogen is further left, it has the least electronegativity. And that's really how you do it if you just take a look at the periodic table. So this will have the biggest difference because fluorine is pulling the same way in all of these cases. So hydrogen being the least, pulling the least, will make the biggest difference in electronegativity. Hopefully this makes sense. Try one on your own, and then we'll discuss naming compounds in a future lesson.